I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to discuss the topic Link Power Budget of Optical Networks. So, the calculation of link power budget is used to calculate the total losses and so that we can identify whether the proposed system is functional or not. So for optimizing link power budget, an optical power loss model is to be studied and the model is given in the diagram. So in the diagram there is a transmitter, connector, splices, and here LC, there is a term LC denotes the losses at connector, and LSP denotes losses at splices, and QF denotes the losses occur in fiber. And all the losses calculated from the source to detector comprises the total loss denoted as PT in the system. And link power margin considers the losses due to component aging and temperature fluctuations. Usually, a link margin of 6 to 8 decibels is considered while estimating link power budget. So, the total optical loss PT is given by the formula connector loss added with splicing loss plus fiber attenuation and also added with system margin PM. So, this can be represented expressively as PT is equal to 2LC plus alpha FL plus PM, system margin. Here L is represents the transmission distance, that is the distance from the transmitter to the receiver. And now we are going to see the link power budget calculation for an example. So in this example they are asked to design an optical fiber link for transmitting 15 megabits per second of data for a distance of 4 km with bit error rate of 0.9, 10 power minus 9. So here we have to calculate the bandwidth length product first. So here bandwidth length product is 15 MB per second is the given bandwidth and 4 kilometer is the distance. And so it is multiplied, we got the bandwidth length product as 60 megabits per second kilometer. And selecting optical source, we can select LED at 820 nanometer is suitable for short distances because it is only 4 kilometer. And the LED generates minus 10 dBm optical power. So selecting optical detector, we can calculate P in minus FER optical detector is reliable and has minus 50 dm sensitivity. And next we have to select optical fiber. So here the step index multimode fiber is selected. The fiber has bandwidth length product of 10 megabits per second kilometer. So for the given problem and for the given bandwidth and distance bit error rate, we calculated first the bandwidth length product and we selected an optical source as LED, and optical detector pin photo detector FER is also detected because it is reliable, and it is having only minus 50 dBm sensitivity. And after that we selected the optical fiber type. It is step index multimode fiber is here selected, and the fiber has bandwidth length product 100 megabits per second kilometer. And link power budget calculation, we are assuming the losses at the splicing is 0.5 dB per slice, connector loss LC is 1.5 dB, system link power margin is minus 8 dB, and fiber attenuation of 6 dB per kilometer. So now the actual total loss is calculated from the formula 2 into LC plus alpha FL plus PM. So it is calculated as 35 dB. So after calculating actual total loss, maximum allowable system loss is calculated by the formula Pmax equal to optical source output power minus optical receiver sensitivity. So it is 10 dBm minus 50 minus of 50 dBm. So it is 40 dBm. Here the actual losses in the system is less than the allowable loss. So we can conclude that the system is functional and it is reliable. And similarly, in the second example, it is given that a transmitter has an output power of 0.1 milliwatts. It is used with a fiber having numerical aperture of 0.25 and attenuation alpha is 6 decibels per kilometer and length 0.5 kilometer. So here the link contains two connectors of 2 decibels average loss. The receiver has a minimum acceptable power of minus 35 dBm. So the designer has allowed 4 dB margin. We can calculate the link power budget. So for the calculation, source power is 0.1 microwatts, system power is 10 decibels, numerical aperture is 0.25. So the coupling loss is 10 log numerical aperture. So we get 10 log of 0.25 square and it is 12 dB. Fiber loss is alpha f the attenuation into multiplied by the length. So attenuation is 6 decibels per kilometer multiplied by the length 0.5 kilometer. So it is 3 dB. Now the connector loss is calculated and it is 2 times of 2 decibels is 4 decibels. We have used two connectors. So here 2 times is multiplied by 2 decibels. And so link margin PM is 4 decibel. So actual output power is P out is equal to source power minus 2 times of losses and it is calculated at 33 dBm and P minimum is 35 dBm. Here P out is maximum than P minimum, that is P minimum is 35 dBm, P out is 33 dBm, it is minus. So here P minimum is higher, the system will perform adequately over the system operating life. And similarly, a third example, in a fiber link, the laser diode output power is 5 dBm, source fiber coupling loss is 3 dB, connector loss of 2 dB and has 50 splices of 0.1 dB loss. So here fiber attenuation loss for 100 km is 25 dB. We can compute loss margin, APD receiver with sensitivity minus 40 dBm, hybrid FinFET high impedance receiver with sensitivity 32 dBm. So here also the power budget calculation, total loss is connected by calculating the output power, fiber coupling loss, connector loss, and it is calculated as 35 dB and available power to the receiver is minus 5 dBm minus 35 dBm and minus 30 dBm and APD receiver sensitivity is minus 40 dBm, loss margin is 10 dBm, H pin FET high impedance receiver is minus 2 dBm. So the loss margin is 2 dBm. Thank you.